Hello everybody, welcome back to this training on natural language processing. In this video we will discuss about something which is kind of a prerequisite before we move forward, and that is the concept of text similarity. And in order to discuss about the concept of text similarity, we will have to understand what do we mean by a vector space model for representing text data. Now, obviously, it derives its concept from some of the earlier concepts that we have gone through, particularly the document term matrix. And I promise that text similarity or the vector space representation of text data is going to be much more simpler and much more easier to interpret than something that we went through when we were looking at the topic model implementation using latent digit allocation. So all set. So as I was saying that the vector space model for representing text data, it actually derives its concept from something as fundamental as the document term matrix, right? So we looked at the document term matrix representation, and we have looked at it multiple number of times through this training. So it's basically the documents and the terms organized in the form of rows and columns, where the rows are the documents and the columns are the terms, and the number of rows actually equals the total number of documents that you're dealing with, that is your size of your data, your sample size, and the number of columns actually equals the unique number of terms which you have in the data. And it turns out to be an n cross p matrix, n being number of documents and p being the unique number of terms. And the interpretation of the ijth element of this matrix is number of times the jth term appears in the ith document. And we have also seen that we can represent this matrix either using the term frequencies or using the TF-IDF values, but that will be material for the purpose of the vector space model. We can either represent them using the term frequency or using the TF-IDF values, so that won't make a lot of difference as far as the concept of the vector space model is concerned. Now, right from the structure of the DTM itself, if we see, a particular document in the data, let's say the document I, it can easily be represented by the corresponding row of the document term matrix, right? So the document I can easily be represented by the ith row of the document term matrix, and the ith row of the document term matrix will actually give us the counts of how many times different terms have appeared in the document I. And this representation, if you see, is actually something which can be interpreted as a vector space representation, because the ith row of the document term matrix is actually can be interpreted as a p-dimensional vector, right? Because there are p components in it, one component for each term, and it can be interpreted as a p-dimensional vector, and each component of the vector actually represents uh, the presence of one particular term in the document. And how it is represented, how the components of the vectors are calculated. It can either be the term frequency or it can be the TF-IDF. But whichever approach we follow, every document in our data, we now get a representation for it in the form of a p-dimensional vector. And this is basically the underlying concept of the vector space model. So every document is actually a point in a p-dimensional vector space, and p here is the size of your vocabulary, or the number of unique terms in the data. So a few things were very apparent right from the beginning. We have seen that for the document term matrix, particularly uh, P is pretty high, because we tend to have a lot of unique terms in almost all data that we handle. So the vector space representation is actually a very high dimensional vector space more often than not. So we are representing the documents as points in a very high dimensional vector space, the dimension being p. For some of the subsequent illustrations, what we will do is we will try to interpret some of the things geometrically as well, because that gives a much more closer look at how things work out. And for that purpose, we will instead of looking at a p-dimensional vector space, we will try and visualize things in two dimensions, because that is always easier to plot and easier to understand and easier to visualize. So the assumption there will be, we are dealing with data which can be represented in two dimension, which means that there are just two terms in the data, which is pretty impractical in terms of an assumption. That will never happen, but it is just for the sake of illustration, so that you always don't have to think p dimensions, and particularly you can look through some of the geometric interpretations as well. Okay, so as I was saying, in the vector space model, every document that you have is actually a point in the p-dimensional vector space, p being the size of your vocabulary. Now, for a moment, if we make that impractical assumption that there are just two terms, two unique terms in your data, and hence your vocabulary size is two, and hence you are representing your documents in a two-dimensional vector space. So that makes slightly easier for us to plot things out and look at the geometric aspects. So so in this case, the two documents D1 and D2, they can be actually represented as coordinate points, and their coordinates will be the corresponding rows in the document matrix, and there will be just two components out here, because we are assuming there are two unique terms in the vocabulary. So T11, T12, these are the uh, number of times the two unique terms are present in the document D1, and let's say T21 and T22. These are again the frequency of the two unique terms that we have in the document D2. Now, now, the fact that we are trying to represent documents in a vector space model has a reason. The reason is, we want to calculate similarity or dissimilarity between different documents. So we want to define some kind of a measure, and it always helps if you're trying to measure the similarity or dissimilarity across components. It always helps if you can represent them in a vector space, because then you can work out different metrics. So in this case, if we look at some of the no-brainers, so can we think of Euclidean distance as a measure of similarity between the two documents? Now, when we deal with continuous data, continuous features, uh, we often use, if not always, we often use Euclidean distance as a measure of similarity, right? So, let's say you have two segments, and for both the segments, you have the age and the income levels. Then if you are to measure, that how similar or dissimilar these two segments are, you can do something like, take the median of the age and the median of the income for the two segments, and then treating them as representative values, you calculate the Euclidean distance. So that's a pretty accepted and tested approach. But the question is, can we replicate that tested approach for the vector space representation of text data? So in this case, specifically, if we are to find out what is the similarity or dissimilarity between the documents D1 and D2, can we say that this kind of a Euclidean distance calculation will work? Now, before going into the mathematics of it, intuitively, when will we say that two documents are similar or two documents are dissimilar, right? Uh, Obviously, one way of looking at it is if we are talking about if the two documents are talking about similar things, if there are similar things mentioned, the context is similar, and and as a consequence, I mean, if similar things are being talked about in two documents, and if the context is also similar, as a consequence of that, you would find some common words in both of these documents, right? So so conceptually speaking, if I have to measure whether the two documents are similar or not, I can try and measure if there are similar words or similar terms present in these documents or not. Now, that way, Euclidean distance appears to be doing quite fine, right? Because it will look at the presence of different words in the documents, and then component by component it will calculate the difference. And if similar words are present in both the documents, then the component wise differences will be zeroed out. However, if there are dissimilar words present in most of the in two documents that we are comparing, if there are dissimilar words present, then the component wise differences and the square of them will not get zeroed out. We will get some positive values there, and hence the distance will be large. So very easy interpretation that Euclidean distance does help us to a certain extent here, but even though it helps us to a certain extent here, it's not one of the most popular or most commonly used similarity or dissimilarity measure when it comes to text data, and we'll quickly see why that is the case. Now, one aspect about Euclidean distance is its value actually depends on the values of these components for which the component-wise differences are calculated and then squared up. So, if I'm talking about the Euclidean distance between D1 and D2, it will depend on the actual value of these components T21, T11, T22, T12, so on and so forth. So, is it a good thing or bad thing? That is something that we want to assess. Now, let's say in document 2 we do something and we convert it to a different document. But when I'm saying that we convert it to a different document, I'm not changing the context of the document. I'm not changing the subject which is being mentioned in the document. All that I will do is I'll simply double the frequency of the term T21. So if T21 was the frequency of a particular term in D2, I will just make it twice. So 2 times T21. So if I do that, what will happen if I do that? So let me quickly try and draw and explain what will happen if I do that. So if I just double up the frequency T21 and keep T22 as the same, then the document D2, it will have a different coordinate representation in the vector space model, right? Because obviously the coordinate points will change. But and what kind of representation will that be? The x coordinate gets doubled up and the y coordinate remains the same, so it will shift towards the right. So it will look something like this, right? It will look something like this, and pardon my drawing out here. So it will look something like this, and we can call this as maybe D. Okay, so it's very apparent that the Euclidean distance between D and D1 will be much larger than the Euclidean distance between D1 and D2, right? Even though D and D2, I haven't made a lot of semantic change in it, in the sense that I haven't changed the context of the of what is being mentioned in the document, or I haven't added new words or new sentences. All that I have done is I'm saying that if one particular word was present twice in the document D2, I'm repeating the same word two more times. So I'm making its word frequency as 4. Just by doing that and keeping the sense of the document intact, I see that the vector space representation of D2 gets shifted, and as a result of that, if I use Euclidean distance as a measure of similarity, the Euclidean distance between D1 and D2 also increases. So which is not an ideal scenario, because Euclidean distance in this case, by the very definition of it, it's getting scaled up between D1 and D as compared to D1 and D2. But if you think between D2 and D, there is not much of a semantic difference or not much of a difference in the context of the subject, just that one particular term has been repeated and its value has been doubled up. So you shouldn't have the similarity. So the similarity measure should not suffer because of that, right? So that is one reason why Euclidean distance, even though it satisfies the mathematical expectations as far as the distance measure is concerned, but because text is slightly different, I mean, it has a meaning associated with it. I mean, just because in a sentence, if a word was present twice and you add some grammatical structure, restructure to the sentence, and increase the frequency of the word from 2 to 4, it doesn't mean that the context of the sentence will necessarily change. Actually, more often than not, it will not change. But uh, a similarity measure based on Euclidean distance will not be preserving the fact that the context has not changed. So what do we do? So let me strike this off. Okay. So we see that something which was very familiar doesn't work here. So what works? So and what works will be something very intuitive as well. So if you look at this diagram, can we think of can we think of angle between D1 and D2 as a measure of similarity between the two documents? And that is exactly what uh, gets used in most cases, because if you use the angle between D1 and D2, that is less affected by the term frequencies than what you see in case of Euclidean distances. So as a convention, we use the angle between the D1 and D2 uh, as a measure of the similarity. And we'll come to a more formal definition of that. But this is actually a representation of the vector space model in a three-dimensional space. So the earlier one was 2D. Higher dimensions than 3 would be very difficult to plot. So parking it. But even in three dimensions, you can represent every document as a coordinate point, and the concept of angle between the vectors, so the angle between the coordinate points still work in three dimension as well as in higher dimensions as well. Okay, so let's now formalize the definition of similarity, or what is often called as the cosine similarity between the two documents. So and the concept actually comes from the dot product of vectors. So if you look at, there are two vectors A and B. A dot B is nothing but the norm of A and the norm of B times cosine of the angle between the two vectors. So that is how the dot product of two vectors are defined. So uh, you calculate the length of each of these vectors A and B by the norm and multiply them, and then you multiply that with the cosine of the angle between the two vectors, and this cos theta can actually be then calculated as as the dot product divided by the length of the vectors, right? And this gives us a measure of similarity or dissimilarity, whatever you may call it, between the documents. And what are A and B in case of the document matrix? A and B are nothing but they are different rows of the document matrix. Or in other words, A and B are the vector representation of different documents in the document matrix. So, and what will be the dimension? The dimension here will be equivalent to the vocabulary size. So dimension of A and B will be equivalent to the number of unique terms that you are dealing with. So you know, if you know A and B, which you will obviously know because you know the document term matrix, you can calculate the dot product, uh, and you can get the cosine similarity measure, right? Quite simple. Now, and it's fairly popular, and in most cases, it's used as one of the similarity measures when it comes to measuring similarity of text data. But having said so, there are other similarity measures as well. But obviously, cosine similarity is the most popular one, and one of the reasons being it's a very simple model based on linear algebra. I mean, it's very simple and very easy to understand, easy to interpret kind of a model. And there is a it's not just an algebraic representation. You can also interpret it geometrically. So that makes it perhaps that gives more confidence to people that there's something which indeed works, and it's quite popular. And the other thing is, it gives you a it gives you a continuous measure of similarity uh, across documents. So cos theta, so it's bounded between -1 and +1, and it gives you a bounded and continuous measure of similarity, very similar to what correlation coefficient gives us, but in a completely different context. But cosine similarity also gives us the same aspect. And it is as a representation model, or as a method for calculating similarity. It's a very scalable technique, and we'll see later how and why this is scalable. And in terms of some of the drawbacks of the cosine similarity, there are indeed some. So the first is, the long documents tend to have very poor similarity values, and this is the example that we were seeing with the Euclidean distance. So cosine similarity mm, solves it to a certain extent, but not to the full extent. So if there are two documents which are fairly lengthy and have lots of words in them, then even though the context is similar, it is likely that the exact words will not be present in exact same words will not be present in the two documents, right? So there can be different variants of the words, different variants of the phrases, and that will lead to a poor similarity value, because the vector space model depends on the exact occurrence of the word. So two documents will be similar if the exact same words are present in both the documents and have similar kind of frequencies. It is not, and the second point that I'm mentioning out here is very important, and that will lead us to one of the later things that we will go through in this training. Cosine similarity is not semantic sensible in the sense that if there are two sentences which have the same meaning, have the same context, but they are expressed in different ways, then they will turn out to be dissimilar sentences if we measure their similarity using cosine similarity. And this is a major drawback, because in every language there is no one unique way of expression, right? The same thing can be expressed in different ways using different words, different phrases. But as far as the cosine similarity measure is concerned, if the words are different, phrases are different, expressions are different, then even though if the context is same, it will show the two documents to be dissimilar. So if I'm saying that, I'm a car dealer versus if I say that I own an automobile business, the cosine similarity between these two sentences will turn out to be very, very dissimilar, even though uh, they're pretty much the same thing being talked about. So the fact that car and automobile are the same thing, and dealer and business kind of have the same connotation, will not be picked up by cosine similarity as a measure. And the third thing is the order in which the document the terms appear in the document does not impact the vector space model. So it's pretty much ordered invariant, which is, and some people may call it a advantage rather than a disadvantage, because if you say a sentence in an active voice and then rephrase it in a passive voice, then the meaning doesn't change. But again, uh, language is a very complex thing, right? I mean, you can change the order of words, and change and that can change the meaning of the sentence as well. So this can at times be disadvantage of cosine similarity. The last point is once again quite severe as a disadvantage, and that will again lead us to something that we will discuss in one of the subsequent videos. So cosine similarity assumes that the terms are statistically independent. And in fact, I would say that it's not particularly a drawback of the cosine similarity as such, but it's an equally a drawback of the vector space model as well. So in fact, I should have mentioned this uh, a while ago as well, that some of these drawbacks that we are talking about here, they are not specific to cosine similarity, but they are in fact drawbacks of the vector space model as well. So the last point that I was mentioning is this representation, the vector space representation, assumes that the different terms which are present in the document are statistically independent, which doesn't sound intuitive enough, because um certain words are more likely to be present when some specific context is being talked about. For example, if you're talking about sports, then words like winning, losing, victory, uh, competition, championship, and obviously the name of the sports. These are more likely to come, right? Rather than if you're talking about politics, then there are a different set of terms which are more likely to occur there. So in a collection of documents, or in a collection of data, uh, if it is heterogeneous enough that you are handling, let's say, a data set which has news articles from both sports and politics, and your assumption is that words are independent of each other, uh, that's not a fair assumption, because mm, the words which pertain to sports are more likely to occur in certain documents and less likely to occur in the documents which pertain to news from politics. So this assumption is also not always very intuitive. Okay, but having said all this, in most cases, cosine similarity and the vector space representation does work. Wherever it doesn't work, uh, there are ways to handle the disadvantages, and one of the ways being latent semantic analysis, which we will look at in one of the subsequent videos. Now, in one of the slides, I was saying that the the vector space model is scalable. And what do I really mean when I say that it's scalable? Or rather, what can make it non-scalable, so to say? So, if you see, the vector space model is actually representation in very high dimensional space, right? Because the number of unique terms or the size of the vocabulary is typically very large. So, as your data increases, you get more and more text, more and more words. Your size of the vocabulary is also likely to increase, right? because if you get more words, then the number of unique words which you are getting is also likely to increase, and that will kind of increase the dimension of the column dimension of the documentum matrix, and hence it will also increase the dimension of the vector space where you are representing the documents. Now, this is a study which was done by a gentleman called Hibbs, and in the Hibbs law, it shows that as the term count increases, as you keep getting new data, the size of the vocabulary, which is basically number of unique terms, it tends to flatten out after a certain point of time, and that's a big relief, because it means that if you keep adding more and more data, then beyond a certain point of time your vocabulary size actually stabilizes, it doesn't explode. Now, what does that mean? It means that as we see more text, more and more new text data, more and more new documents, new sentences, it becomes increasingly rare to encounter words which you have previously not seen. So so beyond a certain point of time, as you see more data, you kind of get back, you kind of keep seeing the words which you have already seen before. And if you are seeing words which you have already seen before, then that doesn't add to the vocabulary size, right? Because the vocabulary size depends on the number of unique words that you are dealing with. So, so that's quite a relief, and quite an interesting and elegant result, which actually makes the vector space representation quite scalable. So it means that if you're working with tons of data, beyond a certain point of time, your data will grow, your number of terms will grow, term frequencies will grow, but the number of unique terms that you are handling with, which is the size of your vocabulary, that will not grow, that will kind of flatten out after a point of time. So which makes working with the vector space model representation on large collection of text data possible. Otherwise it would have been pretty difficult. Okay, so that brings us to the end of the discussion on the vector space representation of documents and the concept of text similarity. And as I was saying right at the beginning, this was kind of a prerequisite before we can get into some of the topics for some of the further topics for this training, particularly the latent semantic analysis. So stay tuned for that. We'll be back with discussion on the latent semantic analysis. Hope you have enjoyed this video. Thank you for watching. Goodbye.